Hello everyone, I'm Chris McIntosh. I help teach the statistics courses, and this week we're going to talk a bit about logistic regression. Since we do not have a lot of information in your heavy text and no chapter in Navarro, I pulled information from another textbook called Discovering Statistics Using IBM SPSS Statistics. A physical copy of this is available at the University of Utah Marriott Library. This is probably my favorite statistics text. It has the best balance between explaining theory and describing how to conduct and interpret a test. Even if you're not using SPSS, I use this in my classes, even if we're not using SPSS, because the explanations are better than any other text I've seen as far as that balance. A lot of texts either hit the theory really hard and leave you hanging with not really sure how to do it in a statistical software, or they hit the software and don't really explain what things mean. So this is a really good text, and this 6th edition came out in 2024, I believe. So logistic regression is used to classify into a categorical outcome variable. If it's two categories, then it's a dichotomous outcome. We call that binary logistic regression. It can be used for more than two categories. They call that polychotomous logistic regression. But most people, the vast majority, are really only trained to do binary logistic regression. The problem comes up using a categorical variable. You might wonder, why don't we just use regular regression? And our linearity assumption gets violated using a categorical variable. So one of our assumptions is that we have a linear relationship between a predictor, a continuous predictor, and a continuous outcome, and that gets violated. So we'll talk in a second how we deal with that. Just as a reminder, here's the formula for linear regression. Remember, we have our predicted y value is equal to b naught, which is the intercept, which is basically the mean of the outcome variable, plus b1 x1, and then the more predictors you have, you'll add another slope and variable and some kind of error term. You don't need to memorize that formula, it's just there to jog your memory, because it's going to come up again. The formula for logistic regression differs from the formula for linear regression. Now we use a logistic function, and I put the formula up there, and that'd be read as the probability of the outcome is equal to 1 over, and then this big term, 1 plus e to the negative b naught plus b1 x1 plus b to the n x to the n, and an error term. So this term that in the exponent looks just like our regression formula, just it's not a direct line now. We're using exponents. And so, yeah, the math is not fun, and you don't need to know the math. So this is all you're going to get into the math. I just put it there to be complete. So to make results interpretable, we really focus on the odds of an outcome. And the odds are written as the exponentiated b. So for the intercept, it's the exponentiated b naught, or b0 is the odds of an outcome when all the predictors have the value of 0. And then you would just keep going through the different predictors. Exponentiated b1 is the proportional change in the odds of the outcome when the predictor increases by 1 unit. And they're all done that same way. And you'll notice in here it says, and all the other predictors are fixed. So in a regression, you increase one variable and all the others are held constant. And that's how you interpret those things. So we really focus on these odds ratios in logistic regression. The exponentiated b is called the odds ratio. It is the ratio of the odds after a unit change in the predictor to the odds before the unit change. It is the proportion change in the odds. And if the odds ratio equals 1, it means there was no change. Things stayed exactly the same. If the odds ratio is greater than 1, then the top half of the equation is greater than the bottom half. The odds of the outcome increase as the predictor increases. There's a positive association between the predictor and the outcome. If the odds is less than 1, then the top half of the equation is less than the bottom half. The odds of the outcome decrease as the predictor increases, and there's a negative association between the predictor and the outcome. And I highlighted this in yellow. Memorize this. This is the most important thing you need to remember about logistic regression in this course, is how to interpret these odds ratios. Logistic regression parameters are estimated by something called maximum likelihood estimation. It's abbreviated with MLE, and you don't need to know how that works for this course, so I just tell you to be complete. We still look at overall model fit in logistic regression, so we look at a couple different things than we did with multiple regression. So there's something called a log likelihood statistic, and large values for the log likelihood indicate a poor fitting model. We have another thing called the deviance statistic, and all the deviance is -2 times the log likelihood. It's also called the -2 log likelihood, and it is used more commonly in than log likelihood because it has a chi-square distribution. So that's some statistical properties that people like, and we often use that to compare models with each other. So we're not going to do much model comparison. I'm just telling you here so that, because you're going to see that with logistic regressions, you don't need to do anything with it right now. So let's talk about R in logistic regression. Because of the way it's calculated, R is not reliable in logistic regression. We still want to know R squared and our percent of explained variance. So we have a couple different ways that they estimate that. And Cox and Snell R squared is a low estimate, and Nagel-Kirky R squared is a high estimate. We're not going to get too much into it. When we get into Jamovi, you're going to see one called McFadden's R square. I actually didn't learn about that one when I was a student. And when we do this computer assignment, we're going to get Cox and Snell and Nagel-Kirky. And when you report that, you just say the R squared is between the low value and the high value. And when we run McFadden's, you'll see it's right between the two. So it's kind of a middle of the road estimate. That's as probably good as anything else, giving them a middle of the road estimate. So we still check our test assumptions before interpreting our results. With regression, we call that regression diagnostics or model checking. We still have a normality assumption, so we'll check the normality of our data, using our histograms and box plots, and we can get our QQ plots and our Shapiro-Wilk test. We want a categorical outcome variable instead of continuous, but the predictor can be any level of measurement. The sample is randomly selected from the population. That's something you know from the study design. What was their sampling method? And our linear relationship changes, and now there is a linear relationship between the continuous variable, a continuous predictor, and the log odds of the outcome. And just be aware there is a linear assumption. It's just that we're using logarithms now instead of regular linear equations. Observations are independent of each other. We know that from the study design. Homoscedasticity, where the variance at the low end of a variable is the same as the variance seen at the high end of the variable. We still want uncorrelated predictor variables. So if we have several continuous variables, they should be not highly correlated with each other. A good cutoff is about 0.8. But we also can get the variance inflation factor, or VIF. And as long as we're down below 5, we're in really good shape. And we still look for bad outliers, and it's those high influence cases, the ones we get with cook distance greater than 1, that we'd be concerned about. So I did put the high influence cases, just the types of outliers. We can have outliers that have a large residual, or we can have outliers that are farther away from others. They call that high leverage. But the ones we really care about when they have a high leverage and a high residual, those are the high influence outliers, and those are the ones we really care about, and those are the ones that Cook's distance will identify for us. So we want a value, if a value is greater than 1, then it's problematic. So we want to be below 1 for that. There are a couple problems that are unique to logistic regression. We're not going to dig into this deep, so you really don't need to focus on this too much, but I put it here just to be complete. Just be aware that there's something called incomplete information from predictors. So we're dealing with categorical variables here, and we want data that represent all the different category combinations that are possible. If you have categorical outcome and categorical predictors, you can make a little table with those like we saw with our chi-square, and you'd want to have people that represent, or observations that represent, all the different categories. If you don't, then that can be problematic for a logistic regression. And then there's something called complete separation. If a single variable or a combination of variables exactly predict the outcome, then your logistic regression won't work. And so you don't want a perfectly, a combination, a single variable or a combination of variables that perfectly predict your outcome, then the logistic regression won't work. There just has to be some variation and variability in there. So sometimes that can be a problem. And they basically, you'll see this when you have too many variables are used to predict too few cases. And the solution is either keep collecting more data or use a simpler model, take some variables out, because it's doing a perfect job, and that doesn't work for logistic regression. We still focus on these two main parts of the analysis. Remember that we look at the model overall, and then we look at the parts of the model, the variables in the model. So I left this slide in from the last lecture, and all these different types of regression, we look at some different things as we're seeing. We have some different metrics that we use to measure things, but we're still going through that two-step, look at the model, and then look at the variables in the model, do it twice. So we're going to go through the steps for null hypothesis significance testing for logistic regression in the computer assignment, but these are our steps that are in the checklist. We're going to select our correct test, identify the independent, dependent variables and level of measurement for each one, check our assumptions. If data meet the assumptions, we'll go through our null hypothesis significance testing steps and interpret the output, once for our model and then once for the variables in the model. Checking our post hoc tests and assumptions, and then we can look at our effect size. So again, with logistic regression, we're going to be an estimated R squared, and you'll just report both Cox and Snell and Nagel-Kirkes. And for the variables in the model, we're going to look at something called the Wald statistic. So instead of a T, like we used in multiple regression, we're going to look at a Z statistic. It's called the Wald statistic. But we still get a significance test, and we can still get a significant test for each variable. So we're going to go through and see which variable is B not equal to 0 and is significant in the model. And that's all I have for this lecture, and we'll see you guys for the computer assignment in a little bit.